Okay, so if you remember last week, we watched a video during lecture, and it talked about some things that we had just covered and also kind of gave us a preview of what we're going to cover today. So most chemical reactions occur in several steps, not in a single step. Chemical equations generally just show the substances that are present at the beginning of the reaction, the reactants, and the substances that are present at the end of the reaction, the products. But there may be several steps that happen in between. And so what we call a reaction mechanism is the series of individual chemical steps by which that chemical reaction occurs. So those individual steps are called elementary steps, and those represent the exact species that are actually colliding in the reaction. So if we look at the reaction between H2 and ICl, this is the mechanism for that. It has two steps. So in the first step, a molecule of hydrogen collides with a molecule of ICl and forms HI and HCl. In the second step, this HI molecule collides with a second ICl molecule and forms HCl and I2. So these individual steps are going to add up to the overall chemical equation. So we can add these chemical equations together. We can look and see if there's anything that appears on both sides. So here, HI is over here and HI is over there. So those are going to end up sort of canceling each other out, right? And then we've got H2 gas on the left and 2 ICl gas. And then over on the right, we've got 2 HCl and 1 I2. Almost forgot the 2. See how those add up? We did do stuff like that in 1A. This guy right here is called a reaction intermediate. This is a substance that gets formed by one step, and then it gets destroyed by another step. So the molecule HI doesn't show up as a reactant or a product, and yet it is present during the reaction. So that's a reaction intermediate. Intermediates get formed in one step and consumed in another. They're like a temporary kind of deal. Any questions yet? So the mechanism is our detailed description of what happens at the molecular level. It's showing us the individual collisions that need to occur. Chemical kinetics helps us figure out what the mechanism is. Determining the mechanism for a reaction can be very difficult. We can't just zoom in with some ultra-powered microscope and see what's happening, right? Because everything's too small to look at. And so we have to use other ways to find out what's going on. And chemical kinetics can help us because we can measure the kinetics of the overall reaction. That's what we've been studying in Chapter 15 so far. And then we can take that and work backwards to find a mechanism that will be consistent with the observed kinetics. Does that mean that that's going to be the correct mechanism? Not necessarily, it's just a possibility. So rate laws for elementary steps are much easier than rate laws for overall chemical reactions. These steps are characterized by the number of particles that are involved in the step. That's called the molecularity, how many molecules. So in a unimolecular step, there is one molecule involved, and that is reacting, generally decomposing, coming apart, and forming products. A bimolecular reaction, we're going to have two different molecules that are going to collide with each other and form products. It could be two of the same molecule, or it could be two different molecules. So both of these are called bimolecular because it involves two molecules colliding. It's also possible to have a termolecular step in which three particles collide simultaneously. Those are very rare. We talked about for a collision to be successful, there has to be enough energy, right, in the collision, and the molecules have to be oriented correctly. If the wrong ends hit each other, it doesn't matter how hard they smash into each other, it's not going to react. So you can imagine in a termolecular step, now we need three things. We need the right three molecules. They have to collide with each other at the same time with enough energy in the correct orientation, right? It's almost like a unicorn, right? It's just like really hard to have that happen. So really rare. Most elementary steps are either unimolecular or bimolecular. So rate laws for the elementary steps can be deduced from their equations. Rate laws for chemical reactions cannot, okay? And so this is kind of dangerous because we like this, it's easy, right? And so then we want to do this everywhere. You can only do it for elementary steps. Elementary steps are going to be the steps in a mechanism, not the overall chemical reaction. So the molecularity of that elementary step is going to equal its overall order. So the rate law, the rate will be equal to a rate constant times the concentration of each reactant raised to the power representing how many of those molecules are involved. So here we have one reactant, and so this was going to be a first order reaction. This step will be first order. Here we have two molecules of A that need to collide with each other. The molecularity is 2, and so the rate will be rate constant times A squared because it involves two of those. Here we have two different reactants colliding, right? And so here the rate is equal to the rate constant times the first concentration times the second concentration. And then here are examples of those rare termolecular elementary steps. And I just want to caution you again, and I'll probably say it at least one more time. We like this because it's easy, and it kind of goes along with what we've learned about things before, right? We're always using the coefficients in the balanced chemical equation to do stuff. And so with rate laws, we naturally want to use those coefficients. You can do it for an elementary step, only for an elementary step. And there will be a question on the exam that asks you to find the rate law, and you're going to be tempted to do this with the overall thing, and that's going to be one of the choices because I know students want to do that, okay? But that's not how we do it for the overall chemical reaction, okay? Just want to be real clear about that. So usually one of those steps is a lot slower than the others, and that's called the rate determining step because it limits the overall rate of the reaction. So the first step might be really fast, and then you have a slow step in the middle, and then you have a really fast third step. Well, the reaction can't go faster than the slowest step. The example the book gives is of construction on the highway. So, they're doing some construction here, and so we go from 3 lanes of traffic down to 1 lane. Cars are, zooming along here before, and once you get past this, you can zoom along again. But right here where everyone's merging down, this is the bottleneck, right? This is where everything slows down. This limits the rate of travel for everybody because we have to go through this one slow step. Any questions about that? So let's look at this example reaction, NO2 plus CO. So the experimentally determined rate law is rate is equal to K times the NO2 concentration squared. So this is the rate law for this reaction. Notice that it does not match the coefficients, right? How do we get this from that equation? We don't. You have to do experiments. You have to change the concentration of the different things and see how the reaction rate changes, and then you can figure out what the rate law is. Could this be a single-step reaction? Well, if this was a single-step reaction, that would mean that this is an elementary step, and that this reaction involves one molecule of NO2 colliding with one molecule of carbon monoxide. If this was an elementary step, what would we predict the rate law to be? Elementary steps can be predicted from the equation. It's possible that this could happen as an elementary step, and so then the rate would equal the rate constant times this to the first power times that to the second power. That's what's predicted if this is an elementary step. But that's not what was determined. So this is not correct. Could this be a single-step reaction? If this was a single-step reaction, if this was the only step that happened, this would be an elementary step, and then these two rate laws would have to agree with each other. Because they do not agree with each other, we can determine that there's more going on here. It's not just one of these colliding with one of those. Any questions? So here is a possible mechanism for this rate. Yeah. How do we know it's not just one step? Great question. If this was one step, the rate law would be this. Yeah, so an elementary step, a single-step reaction, would involve one molecule of this colliding with one molecule of that. And that will always give us something that looks like this. The reason that the experimentally determined rate law for this does not match this is that we've got something like this going on, where we actually have two NO2s bumping into each other, making an NO3 and an NO. I mean, who would have guessed that that was going to happen? I wouldn't. And then this NO3 bumps into a CO and makes NO2 and CO2. And so then this NO2 and that NO2 just don't show up in the overall reaction. And this NO3 doesn't either. Okay. If this was just one of these colliding with one of those, this would be the rate law. And we would determine that experimentally and find out that that's true. That makes sense? It's kind of confusing. Kind of. Yeah, you're like, oh, yeah, she tried. It's still not okay, but she tried. Any other questions? So this is a possible mechanism. In the mechanism, each of these is an elementary step. Here, the first step is slow, and the second step is fast. The slow one is what determines the rate. Once it gets past this step, it just zooms off, right? It has to get through this first. What's the predicted rate law for that slow step? NO2 squared. We have essentially two NO2s, and so we have NO2 raised to the power of 2. And this is what I, cautioned you over and over again. We can't do that. we can do that for an elementary step. So this elementary step, which is the slow step, gives this rate law. This matches the experimentally determined rate law for the chemical reaction. Well, what about this one? Doesn't that one come into play? No, it doesn't, because this is what limits the rate. This goes faster, and so it doesn't have any effect on the rate. Any questions? It's kind of weird.
How will be able to identify this in each equation?
An elementary equation? How we identify an elementary equation?
No, that any equation will be able to identify the rate for any equation, like
You cannot determine the rate law for just any equation. You can only do it if it's an elementary step. How do you know it's an elementary step? Well, it would have to be part of a mechanism, or we would have to say this is an elementary step. You can't tell looking at this chemical equation if it's an elementary step or not.
so when you said it's gonna be like something as an exam in the exam. So you mean the elementary step gonna be not the official equation?
Yeah, so in this example, the first step is the slow one. And so we can figure out this rate law knowing the mechanism. But if I just give you this equation and maybe some data and say, what's the rate law? You can't just write this, because this is not an elementary step. Okay? Yeah. That's a great question. You have to determine the mechanism. Generally not. So what we're going to see is that there's some qualifications for an acceptable mechanism. One of those is that if you add the steps together, you get the actual chemical equation, right? So here, those are going to cancel out, and those are going to cancel out. And so when we add these two steps together, we get the overall equation. If these added up to something else, that would just be an obviously incorrect mechanism. You could come up with lots of different mechanisms that will add up to the correct equation. Some of them could be like really, really insane. Like you could, throw in some Martian element or something in here that doesn't even exist on Earth. And, you make this thing and then it disappears again. And so it cancels out. And so your overall reaction looks okay. Yeah, no, you can't do stuff like that, right? But, there's lots and lots of different possibilities for the mechanism and have it still add up. The other thing that has to happen is we can deduce a rate law from the mechanism, and that needs to agree with the experimentally determined mechanism. So let's look at that. Well, I guess we'll look at that in a minute. So in that example, the first step has a higher activation energy, and so it has a smaller rate constant, and it has a slower rate. So here, it takes this much energy to get up to this first transition state. Once you get there, it's downhill. Right? So if you imagine like a roller coaster, and the chain or whatever is pulling you up here, once you get up here, your momentum is going to carry you the rest of the way, right? You come down here, and yeah, you have to go up a little bit, but you got plenty of energy to get over that and get all the way down. You're just racing, right? But this is the slow step. This is what limits how fast it goes. And that's because of this higher activation energy. So in this example, because the first step is the slow step, The first step determines the overall rate, and thus it predicts the same rate law as the experimental data. And so that's what we saw here. This slow step predicts that this would be the rate law, and that matches up with the experimental data. Yeah, so we're going to look at the slow step, and we can almost always figure out what the rate law is from the slowest step. It's not always this simple. Yeah. Any other questions? Yeah.
On the next slide, it says those transition states.
What are those? That's a great question. So the transition state is where we have those, here we had the NO2s colliding, and they, when they are together in that collision, they are in the process of becoming NO3 and NO, and that's a transition state. So it's like this teetering point, right? So when those guys run into each other, now it's possible that the reaction doesn't occur and they go back to what they were, but it's more likely if they had enough energy to get up there, then they will continue to react, and so then we'll get the NO3 and what was that? The NO. So we'll get these two guys. And then in the next step, we need the NO3 there to collide with a CO. And that will have be its own transition state, but that doesn't require as much energy. And then it goes. Any other questions? These energy diagrams are the best we can do to make this very abstract idea visual, right? So conditions for a valid mechanism, the elementary steps have to add up to the overall reaction, and the rate law predicted by the mechanism has to be consistent with the experimentally observed rate law. Like many things in science, we cannot prove mechanisms to be correct. We can validate them. We can say, okay, all of the evidence suggests that this is correct, but we can't prove anything to be correct. It's really a bummer when you think about it. We can prove things wrong, but you can't prove anything right.
So will the question on the test be if this is a valid mechanism or not?
Yeah. So a possible exam question would be giving you, this is the overall chemical reaction, this is the experimentally determined rate law, is this a valid mechanism? And so the two conditions, you'd have to determine, when I add these together, do I get that? Yes, I do. Okay, check off condition 1. Is the rate law predicted by this, does it match the experimentally determined one? Yes. So this is a valid mechanism. Doesn't mean that it's the correct one, but it's possible. Any other questions? So that was a mechanism that had a slow step at the beginning. What if the first step is fast and the slow step comes somewhere later? Well, if that happens, then the rate law predicted by the rate limiting step might have some reaction intermediates in it. All right, let's just go back to this one real quick. Whoops, not that far. If this was the slow step, what rate law would we predict?
Also for this one.
Pardon me?
Also for this one.
Well, we're going to pretend that these are reversed. Just pretend.
Okay then.
So then this would be the concentration of NO3 and the concentration of CO. Right? Because We can predict a rate law from an elementary step. And again, we like that so much, we want to do it all the time. You can't do it all the time. Just the elementary steps. Could this be a rate law for that chemical equation? No, because it's got the concentration of NO3. There's no NO3 up here. NO3 isn't one of the reactants. This is an intermediate. So now we have a problem, right? When the second step is slow. So if the first step is fast, it may establish an equilibrium. And you have learned about equilibrium in the past, but you may not remember exactly what that is. Most chemical reactions can go in the forward direction and in the reverse direction. We kind of, keep it simple in Chem 1A, and we had a lot of just forward arrows, and we just kind of assume that everything reacts until it's done, and now we're going to break your bubble, and that actually doesn't happen much at all. So the reactants can react to form the products. The products can also do the reverse and reform the reactants. An equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. And so at equilibrium, it looks like nothing's happening because the concentrations of reactants and products are the same as they were 5 minutes ago. But it's actually very, very busy in there. You have reactants reacting to make products, and you have products reacting to make reactants again. It's going back and forth. You think of it as like a busy airport in the middle of the day. So, maybe there's 5,000 people in the airport at noon. And at 2 o'clock, there's still roughly 5,000 people in the airport. Are those all the same people? I hope not. Or, maybe there's a bad snowstorm or something. But usually those are not the same people. Because airplanes are taking people and leaving, and other airplanes are bringing people. So you got the same number of people, but it's different people, right? If the rate of people leaving and the rate of people coming in is going to be the same number, as long as those rates are equal, but it's not the same people. Okay, so that's one picture of an equilibrium. Okay, so let's look at a mechanism with a fast initial step. So here is our overall reaction. We've got hydrogen reacting with no, and here's our observed rate law. This is the mechanism. The first step is fast, the second step is slow, the third step is fast. So first, let's show that condition 1 is met. Do these 3 steps add up to give us that? Well, let's add them up and see. So before I write stuff down here, I'm going to look to see if these are almost like spectator ions, right? They appear on both sides. What's happening, this is an intermediate that gets formed in the first step and destroyed in the second step. So it doesn't show up in the overall equation. So we don't need to show that guy. And then here's N2O and N2O. So that's being made and destroyed. And let's see, do we have anything else like that? No, that looks like it. So we've got 2 H2s and 2 NOs. And that's making, let's keep it in the same order. 2 H2Os and 1 N2. See how that works? We did this with like Hess's law, adding stuff together. Yeah. So condition 1 is met. Any questions about that? My question is, what's on the next slide? Oh, okay, cool. So for condition 2, we need to have the rate law predicted by the mechanism be consistent with the observed rate law. So this was the observed rate law. Here we have a fast first step, a slow second step. After this slow step, we don't need to think about anything else that happens after that, right? It's literally all downhill from there. So that's why on this slide, they're just showing us the first two steps, up to the slow step. Well, we can predict a rate law for the slow step, right? So for that slow step, the rate is going to equal a rate constant times h2 to the first. We can assume that this is going to form an equilibrium, and when that happens, the forward rate equals the reverse rate, right? So the rate forward is equal to the rate in reverse for that fast step. Well, we can write a rate law for the forward reaction. In the forward direction, the rate is going to be equal to k times NO squared, right? So forward, we're going to get rate is equal to k times NO squared. Sorry, got an extra 2 in there. So that's forward. And the reverse, the rate would equal a rate constant times the concentration of N2O2. This going to that. So this is forward and this is reverse. Does that make sense? You see how that works? So the reverse rate and the forward rate have to equal each other. Well, that means that what they are equal to has to be equal. So I'm going to call this rate constant the forward rate constant, and this one the reverse rate constant, because they're not going to be the same number. But the rate forward is the forward rate constant times NO squared. That has to equal the reverse rate constant times N2O2. And there probably will be a question on the exam where you have to determine the rate law from the mechanism where the first step is fast. You can definitely get a good grade and pass the class if you don't get this part, but give it a shot, please. So everybody okay with what I did here?
So now what is done?
No, we're not done. We're not even close. No. So this is what we predict from the slow step. Our problem is that it's got this N2O2 in it. And so we're doing this business over here so that we can get rid of N2O2. So we're going to take this and rearrange it to find out, well, what does N2O2 equal? So N2O2 must equal K forward times no squared divided by K reverse. So I just divided both sides by K reverse. So N2O2 equals this divided by KR. So that's what I wrote in here. N2O2 is equal to that. So I can plug that into my equation over here. So there's that equation. I'm getting rid of this, so I'm going to replace that with this guy, because that's what it equals. So rate is equal to rate constant times H2 times K forward no squared over K reverse. So again, this is what I subbed in for N2O2. Well, that kind of looks like a mess, doesn't it? Now we've got 3 rate constants in here. None of these individual rate constants is meaningful at all. What we can do is we can just lump them all together and say, well, it is a constant. We'll call it something else. We don't want to give it the same name as any of these things. So maybe we'll call it K prime. So I'm going to take these guys, and we're going to say, maybe I'll throw that up here, that K prime is equal to K times K forward divided by K reverse. So rate equals K prime H2 NO squared. There is a use for all those rearranging equations things they made you do in math class. Now, you may never need to use them in your actual job, but they definitely have a place. So this matches that. What do you know? Cool. Questions? So that's one of those things that you might need to write some steps for yourself of how do I do this, right? So here we'll do another example. Ozone naturally decomposes to oxygen by this reaction. Here's the experimentally determined rate law. Show that this proposed mechanism is consistent with the observed rate law. So they're not asking us to validate the mechanism. So we can assume that if we add these together, we're going to get that. And I did it yesterday, and it does work out that way. So the steps then are, you're going to look at the slow step and write a rate law based on that slow step. So the rate law predicted by that slow step is a rate constant times O3 times O. The concentration of O3 raised to the power of its coefficient times the concentration of O raised to the power of its coefficient. And again, don't get too comfortable with that. You can only do it sometimes. That's our predicted rate law from the slow step. So that's from the slow step. Now, our job is to get rid of the concentration of O because that's not one of the reactants. So it doesn't show up in the experimental rate law, and it just can't be there because we have no way of knowing what that concentration is. So what we do then is we assume that this fast first step forms an equilibrium, and that means that the forward rate is equal to the reverse rate. So rate forward equals rate reverse. Well, we can predict a rate law for the forward reaction. It's going to be a constant times O3. So we'll call that the forward rate constant, and we've got the concentration of O3. That has to equal the reverse rate, which is going to have a different rate constant, and the reverse reaction, right, will be O2 times O. You see what I did there? You okay with that? So first step was write a rate law from the slow step. The second step is we're going to assume that fast first step forms an equilibrium, and so we're going to write an expression for the forward rate and the reverse rate. They're equal to each other. Now we are going to rearrange this, and we're going to solve for this intermediate. The rate law predicted by the slow step has something in it that doesn't show up in the actual equation, and that's a problem. So we're going to use this to get rid of that. So we're going to rearrange this. We're going to find out that the concentration of O is equal to the forward rate constant times O3 divided by the reverse rate constant times O2. Just rearranging this equation, I'm solving for O. So this business here, then, is equal to that guy up there. So we're going to plug him in. Oops. So rate is equal to rate constant times O3, and then we're going to plug this in for the O. So K forward times O3 divided by K reverse times O2. We're going to gather up all these constants into one and say that this is a new constant, and that's times O3 times O3 divided by O2. Well, as I've written it here, this does not look exactly like that one, does it? But O3 times O3 is O3 squared, right? Rate equals O3 squared. And this O2 is in the denominator. So that 1 over O2 is the same as O2 to the minus 1. And so we come up with a rate law that matches the experimentally determined one.
On the rate law that we were doing before, so there was no mechanism?
On the rate laws that we were doing before?
Yeah.
So before today, there were mechanisms, but we weren't talking about them. We were only using experimentally determined rate laws.
Okay, so this we can demonstrate the rate law by two ways. Either we have the data and
Either you have the data and you look at, okay, well, this doubles and the rate doubles, so that's first order and that kind of stuff. Or if you have a mechanism, then you can figure it out. But it's kind of circular because how did they figure out what the mechanism was? They measured the rate law experimentally, right? So, because that's a really important feature here is you can come up with different proposed mechanisms. But if your mechanism does not predict the same rate law as you experimentally observe, it's not the correct mechanism. Yeah, okay? Great questions. Anybody else? Here's another one, just using A's and B's instead of, all those other letters. So, predict the overall reaction and rate law that results from the following two-step mechanism. So we're saying, here's the mechanism, what's the rate law, what's the overall reaction? Well, let's do the overall reaction first because that's easy, right? We just have to add these together. So those A2s are, this A2 is an intermediate. It gets formed in the first step and destroyed in the second, so it doesn't show up in the overall reaction. So there's the overall reaction. So the rate law is always going to come from the slow step. So we can write a rate law from the slow step of the mechanism. So the rate is equal to K times A squared, because there's two A's here. Okay? Does this have any intermediates in it? No, because the first step was slow. When the first step is slow, it's easy, because that is the rate law. It gets messy when it's not the first step. When the first step is fast, then you have to do all that algebra business. So the rate law then is rate is equal to K A squared. So some things that happen when students take an exam. They did a lot of problems where the slow step was the second one and the first step was fast and it was hard, right? And then they get one like this on the exam, and so they assume that they have to go through all of that when actually they don't. And so you make it way, way harder and you get confused and you may or may not come up with the correct answer. The other thing that can happen is that students, remember this more, and so then you get one where the first step is fast and you still try to do it just by looking at the mechanism, and then you're going to end up with the wrong thing. Okay, so those are pitfalls to watch out for. Any other questions?